Hello, welcome back to another lecture. In this lecture, we're going to go ahead and do a beam design for timber. Take a look at the problem on the board. We have this beam that it is 20 feet long, and we want to know if this beam can support 4,000 pounds down in the center, and that 4,000 pounds is basically a movable load and like a hoist. And then the beam itself weighs about 14 pounds per foot. And the bearing on both sides is 4 inches, and the beam is not laterally supported. And so one of the first things we do, we're going to say, okay, we'd like to use 4x16 Douglas fir large, and to use that, see if that the beam can handle that much weight. So let's go ahead, look at table 1B of supplement NDS. And from there, we can get all the information for 4x16, which the actual size is 3.5 by 15 1/4. And we then write down all those information. And then let's proceed to table 4.31, which tells us FB prime is equal FB times CD, CM, CT, CL, CF, CFC. And this is for ASD design. And then from there, let's go to table 4A. In 4A, we can write all the information for the different stress. Our FB is a 1,500 pound. FV is 180. Which, let me write that down. FV is 180 PSI. And perpendicular to the grade is 625 PSI. And I got to set them down. Module for elasticity 1,900,000, and E minimum is 690,000. So from table 4A, we have all these. Let's look at the adjustment factor. The adjustment factor comes out for most of them. We're going to get like for CB, it's going to come out 1. CD, I'm sorry. CD comes out 1. CM comes out 1. And CT, CF, they all comes out 1 anyway. And so most of them are 1 because it's inside condition and dry condition. And CF also comes out 1. How we find CF? If you look at the table, supplement table 4A, it says for 14-inch and wider, CF is equal 1. And therefore our E prime, minimum, which is equal E times CM CTCI, and that's from table 4.31. So that comes out basically all multiplied by 1, and that comes out to E prime minimum comes out to 690,000, and our E prime gonna come out to same thing multiplied by 1, so 1,900,000. 1,900,000. See if I can write it. Okay, PSI. Oh, I have written down all those. I wasted the thing. So they write down here anyway. Never mind. So now we have all that. Our FB prime. Let's go to FB prime. Comes out to 1,500 times CL, and we have to calculate what CL is. And CL is based on the unbraced length. So let's go to table 3.3, and from that table, I'm gonna erase this here. I already have it over there. Need the board size. Okay, so I have table 3.3. The unbraced length LU is equal. Our LU, the unbraced length, is equal 20 feet, which is same as 240 inch. And now our LU divided by D, and you know what D is because we have a 4x16, so it's 240. It's a 4x16, but the actual size is 15 1/4, so 15.25, and that comes out to 15.7. And per spec is more than 7, so we okay. That means we're gonna use the formula, as you can see on a board. LUE is equal 1.37 LU plus 3D. And if you plug all that in, it becomes 1.37 times 240 plus 3 times 15 and a quarter, and that comes out to 374.6 inches. So now we have that, and we're gonna go ahead and let's find out the slender ratio RB. Take a look what it's on the NDS. So our RB can come out to, the slender ratio come out to square root of LED divided by B squared. You see the formula, I'm not gonna write the formula down. I need board space. So it's 374.6 multiplied by 15 and a quarter, 15.25, and divide the whole thing by B squared, and B is 4 inches, or actual size is 3.5 squared. Okay, now remember 4 by 16 is actual sizes, that's why I have that right there. And so that comes out to, our RB comes out to 21.6, and that's less than 50. Take a look at the spec. Spec says has to be less than 50. We're good right there. The next thing, we're going to go ahead and find FBE, which is the critical buckling design value. So the critical buckling design value, FBE, is equal 1.2 times E prime minimum. So that be equal 1.2 times 690,000, right? I got 690,000, and divide that by 21.6 square, and 21.6 square is from here there, and that comes out to, I did not calculate that. Give me a second, I will tell you what it is. 1,774.7, okay, PSI. So now we have that, and the next step, we're going to go ahead and calculate the CL. And CL is equal, that long formula, I'm not going to write it down, so I'm just going to write the answer down. And you can double check my answer. I get 0.876. 0.876. I might have made a mistake, but double check it. And that's from that long formula. Actually, let me write that down and do it again. CL is equal 6. I might have made a mistake here. Double check. It's not a big number, so that's where I'm going to stop right here. I'm going to clear the board and start over again. So give me a couple of minutes. We have calculated CL and came out to 0.87. We're going to go ahead and say FB prime is equal 0.87 times 1,500, and that roughly comes out to 13, 14 maybe. And so from 3.3, our FB, it is equal, this is based on our load. Remember, this is based on our load. Remember at the beginning I said we're talking about how we're going to size the beam. If we had to size the beam, this is where we're going to go ahead and do it. So FB is equal M divided by SX, and we got to calculate our M. So our M, now let's go calculate our M here. Our M turned out to be, take a look at the load. We have, and if we look at the design formula, we can say our M is equal, I'm going to write right here, it's WL square, W dead load L square plus divided by 8 plus PL divided by 4. And that comes from the equation formula. So that comes out to equal 13.9 times 20 squared times 12. Remember, one of these cancels the other out. That's why I don't have it times 12 twice. and divided by 8 plus, and we have PL was 4,000, and time 20 time 12 divided by 4. So my final answer comes out to 248 and 340. That's going to be it's going to be pound foot. No, pound, yeah, pound inch, or pound inch, okay, sorry, pound inch, because we did multiply by 12. So now that's our M, and we're going to come back in here, so we're going to say M divided by SX. So our M is 248,340 PSI, pound inch, okay, divided by SX. Our SX for that size came out to 135.66, and we're gonna get 1,830.6 PSI, and that's bigger than our 1314, so that is no good. So we know this beam is not big enough for that size. Even if we made CL equal 1, it wouldn't help us. So the beam is way undersized. Let's find out, and if I want to know what size of beam I'm going to use, I can go ahead and just say, okay, I don't know what is this number. I know this is equal this, so I just replace 1314 here, and I have this, and I make this a known value, and I calculate the SX, and then once I have SX, and that's equal easily, you can calculate from there, which is BD squared divided by 6. Now, I want to know, okay, I have this beam anyway, I'm going to use it, but how much weight I can put on it? What's the maximum weight I can support? Let's find out what's the maximum weight I can support. Then we can use that maximum weight that I can support, see if it's going to meet the other criteria. And then for a beam design, we have to check for 4 different criteria. All right, so what we're going to do, we're going to say, okay, FB prime is equal 1314, and that is equal M divided by S, which is, let me write this down. Well, that's basically this formula right here. That's equal M divided by SX, which is equal, I have, I know M, I don't know M, I know SX, okay? So that's equal M divided by 135.66, and therefore my M is going to come out to 135.66 times 1314, and that gives me about M is equal 178,257.25. That's a pound. This is an inch. That's a PS, pound per square foot, and that is an inch cube. So that's come out to pound inch. However, this is just a moment. Let's take out the beam moment out of it. So if I take that minus this value, which comes out to minus 13.9 times 20 squared times 12 divided by 8. So what I did basically, I took the weight of the beam. And you can leave it be, or you can use this, or you can take this out to be more exact. Doesn't matter. So now it comes out to 169,917 point something, 0.2 pound inch. Now I have that. I can go ahead. Let's divide that by 12. Make a pound foot. That way I have 169,917.2 divided by 12. Give me pound per foot, and that give me about 141.60 pound foot. Now I have that. I want to find out what is my maximum moment for maximum load. I can go ahead. So that should come out to equal PL over 4, right? okay? And I know which is equal P, we don't know. L is equal 20, let's go with the foot, divide by 4. So therefore do the simple calculation. Your P is gonna come out to 2832 pound. So the maximum that we can go ahead, P max really should be, and for this problem, 2,800 pound. Let's round it down. So now we know that's our maximum of load we can put on that beam. We're not done yet. I gotta clean this board. Give me a minute. We have that, and assuming the load we had at the beginning was workable, but now we're gonna find out if this load still satisfies the criteria. When we do this beam design, we have to make sure we gotta find out if it's gonna make the bending, if it's gonna make the shear, if it's gonna make the deflection, and then how about the bearing. So we're gonna go all for all those four. So for bending, didn't make it, so we changed the load to 2,800. If we change the load to 2,800, the bending just makes it. So we're gonna use that for now, and this continues, find out for the shear. So based on, so remember, this is gonna be based on P equal 2,800 pound. All right, so now we're gonna go, I said, FV prime from table 4.31, which is equal FV multiplied by CD, CM, CT, and CI. And all those is going to be equal 1, so we're going to end up with 100 PSI. And that came from table 4A, and we already have that. But want to find out what is the reaction. If we have this beam, I'd like to know what the reaction is. I got a load here is 2,800 pound, and I got a beam weight at 13.9 pound per foot, which is not much. So my reaction R1, let's call this R1, which should be same as R2. R1 comes out to simple, we've done this before. W dead load L divided by 2 plus P, which is this BP, divided by 2. You can pick that from the formula, or you can just go back from structural analysis and say that's how we got it. So I got 13.9 times 20, divide that by 2 plus 2,800 divided by 2, and I get 1539 PSI. So that's my shear. And so V, that is my reaction, sorry. So the shear, if you look at the NDS section 3.4.2 and 3.4.3, V, the shear, gonna come out to 1539. You gotta take out the LB divided by D. So because of the load, the uniform load right here. So I got 13.9 times LB divided by 2 plus D. And that comes out to, let's write it out. Okay, so 1539 minus 13.9. LB was 4/2. That must the bearing on a beam itself, and plus 15.25. Divide that by the whole thing. Let's make that by 12 inch, because that's a pound per foot right there. And I'm going to come out with 1519 PSI. Okay, so and FV, our FV, so I'm going to come back here. FV is equal 1 VQ over IT, but because our cross section right here is a square cross section, which is 3.5 by 15.25, and that's a 4. I had a timber design professor many years ago, and if I wrote that down, he would have failed me. He was very particular about the way you write your mathematical number. So anyway, and FV is equal VQIT, but for a square shape like that, this is a square, it's not a, and it's 3.5 divided, or 1.5 times VBD, so it become 1.5 times our V was 1519, and BD is 10.5, is the area of this shape here, which came out to 53.8 from the table, or you can multiply these two by each other, which comes out to 53.8. So that comes out to 42.6, which is way less than 180. So the shear checks out. Okay, shear checks out. Give me a second. I want to erase all this stuff up here. So the next thing we're going to calculate is the deflection. So we pass shear, we got to see if we can pass deflection. Deflection from the formula delta is equal, and we're going to go ahead and we're going to calculate deflection for just for the P, not for the load beam itself. So delta is equal P L cubed divided by 48 EI, and that comes out to 2800 times 20, which is times 12 by power 3, divided by 48 times 1,900,000, and I came out to be 1034, and I get 0.41 inch, and that is less than L divided by 360, which is 240, divided by 360, which is 0.667. We check out. We're good. Deflection, let's check for support bearing. Okay, support bearing, right? Yeah. Okay. See if I can get that, and we found out the reaction force R1, which came out to R2. We calculated in the previous step, and that came out to 1539 psi. And if you look at the table 431, our perpendicular shear was, I got it. I didn't write it down, but I got, no, it is 625 right here. It is 625, but we're going to calculate this in reality. So it's, we're going to say perpendicular is R1 is divided by the bearing length time B itself. So R1 was 1539, divided by LB was 4 inches, and width of our beam is 3.5 inches. So that will give me 110 psi, and which is less than the design the value F prime C was F prime C times CM times CL times CB. All those will equal 1, so it comes out to 625, and this is less than 625 and checks out. So what we did so far, we had the beam. We design, when you design a beam, you got to check for bending, which we did. You got to check for shear. You got to check for deflection, and then you got to check for bearing. Make sure it passes all those. Our beam failed in the first time around, so we said, okay, we're going to change our problem. Instead of 4,000 pounds, we're going to use 2,800 pounds. Then if we use 2,800 pounds, already we were at the bending, so the bending was okay. And then we did the shear and the other three and came out okay. Take care and be well.